Now, this is cubic symmetry, multi-rotation symmetry, which is a little bit complicated. Now, let's think about this tetrahedral group first. Tetrahedral group, by the Schoenfly notation, is 2, 3, 3. In the stereophilic projection, how it looks like is basically cubic system. So we have to define the standard cubic projection. Okay, so this is z-axis and this is x-axis, this is y-axis, and this is, this is one axis. And when it says 2, 3, 3, it has basically threefold, 4 threefold elements in here. Okay, and if one has twofold in here, then this threefold generates another twofold in here and twofold in here. Okay, so this one is twofold and this one is twofold and this one is twofold because there's a threefold symmetry elements here and we have one twofold symmetry in here. Then this two threefold is developed by this twofold operation, but this threefold symmetry should be again defined. So this is what people call 2, 3, 3. Okay. Anyway, if I put the general poles in here, one in here, then twofold generates here, this twofold generates here, and this twofold generates here. Then this threefold generates here, here, and this one threefold generates here, here. Okay, so this one threefold generates here, and then generates here, and this threefold generates here, and this one generates here. And then 1, 2, 3, 4, 5, 6, okay, 7, 8, 9, 10, 11, 12. So multiplication factor is 12. And this is T by Schoenfly notation. And when we define this one, people later call it, okay, this is the cubic system. And we wrote it as 2, 3. We deleted this. When people write this as an international symbol of the cubic symmetry, the first digit designates 100 type axis. And the second digit generates 111 type axis. Okay, so 2, 3 in the standard symbol, meaning that in the cubic symmetry, the first digit means that all the 100 type of axis has twofold, x-axis, y-axis, z-axis in here, and all the 111 axis has threefold. So this is the notation that people using in international symbols. 432 complicate, again belongs to the cubic. So we start from cubic elements. In this case, this 4 is 100, next one 3 is 111 axis, the next one twofold is 110 axis in the cubic crystal system. All right, so there is fourfold, x-axis, y-axis has fourfold, so this one has fourfold, this one has fourfold. So all the 100 type of axis has fourfold. Now all the 111 type of axis has threefold. Now all the 110 type of axis has twofold. So where is 110 type of axis? This is 110, twofold. This is another 110 type, twofold, twofold, twofold. Now this one is twofold, again 110 type, this one is twofold, this one is twofold, this one is twofold. So that's 432, Schoenfly notation is O. All right, so if I put any poles in here, so fourfold generates 1, 2, 3, 4 by the z-axis, and by the fourfold rotation operation, which is 90-degree rotation operation of x-axis, generates 90-degree upper pole, down pole in here. And again, this one generates upper pole, this is 90-degree, 45 and 90 degrees, so down pole generates here. And this one is fourfold, again, upper pole, down pole generates here. This one is upper pole, down pole generates here. And so far, I did only 100 type fourfold operation of x, y, 001 axis, 100 axis, 010 axis. Now I have to do the threefold operation. When you do the threefold operation, it goes in here. Then this one is upper pole, and this one is down pole. And this one is upper pole, this one is down pole. And this one is upper pole, this one is down pole. And okay, this one is upper pole, and this one is down pole. So it has fourfold symmetry satisfies. Okay, this is the end of symmetry operation. You don't have to do the twofold rotation operation. When you look at it, the twofold operation is already there. All the 110 type of axis has twofold symmetry. So what are the multiplication factors? Multiplication factor is 24. Okay, so when you read this Champlain notation and international symbols, you know how to put the symmetry elements in the stereography projection. And when you put any general poles, maximum multiplication generates, then you have to know how to generate these extra poles by this symmetry operation. So far, I finished this part. Now let's go to the single rotor inversion. S4. This is single rotor inversion operation by the Champlain notation. The 4 bar. This is rotor inversion, which cannot be generated by the rotation, mirror plane, and inversion centers. So this should be separately defined. 4 bar. 4 bar is, we did this already. 4 bar is basically when there is one general pole, 90-degree rotation, inversion. 90-degree rotation, inversion. 90-degree rotation, inversion. So these are 4 bar. So this is upper pole of right hand, and this is 4 bar. So this one is left hand, and this one is right hand. So upper pole, down pole, right hand, left hand, rotor inversion. That's something that you have to remember. And when you look at it, you can find out that starting from pure rotation, you cannot generate this by putting any mirror plane or inversion centers in here. So Champlain defines by single rotor inversion of fourfold. So I did this. Now let's go to this CNH. So cyclic rotation operation of n-fold, and I put horizontal mirror plane. Okay, so the first one is CS. This one is basically C1H, one fold, and I put the horizontal mirror plane. But one fold is no symmetry in there, and you have one mirror plane. So this is just one mirror plane. So international symbol-wise, this is the same as this symmetry only has one mirror plane. And Champlain wrote it as S, CS. This is coming from Spiegel, this German word of saying mirror. So Spiegel is German word. So CS is basically the same as C1H, and basically this is the same as mirror plane. Now let's look at C2H. Okay, Champlain notation says that it's a cyclic rotation operation of twofold, and you have horizontal mirror plane. So strap projection-wise, this one has just one twofold and horizontal mirror plane. Mirror plane, certain axis has mirror plane. When you say that, this mirror plane should be perpendicular to that axis. So in this case, I write down the mirror plane like this, And in the stereogram, I might say that there is lattice point in here, there is twofold rotation, vertical axis. Now this one is the mirror plane. And this mirror plane is showing in the strip projection as the dark lines in here, as a big circle. That's the C2H. And symmetry-wise, if you put general pole in here, then twofold generates here. And there is mirror plane. For instance, I have one pole in here, twofold generates another pole in here. But there is a mirror plane, so there is a down pole in here, there is down pole in here. And that's the same location in here as the down pole. And this upper pole has right hand, and this down pole all has left hand. Right hand, left hand, because this operation is incongruent operation, enantiomer operation, and that is developed by the mirror plane operations. Okay, so this is C2H. International symbol-wise, this one axis has both this vertical axis has both twofold, and this y-axis has mirror plane, because mirror plane is perpendicular to that axis. So we define that this axis has both twofold and mirror plane, and international symbol-wise, we wrote down like this. It means that one symmetry element has both twofold and mirror plane. Again, when it has mirror plane, twofold, 180-degree rotation components in there, and there is perpendicular mirror plane. And in the theorem-wise, we know that immediately that there is inversion center in here. Okay? So there is inversion center in here because this is inverted, inverted. This is inversion, inversion, that's matched. So 180-degree rotation operation and mirror plane matches that there is an inversion center at the point of where the lattice point locates. So C2H has inversion center naturally developed. C3H, okay, this is just the threefold principal axis. This one has threefold. Now it has horizontal mirror plane, so there is a mirror plane in here. Now the general pole generates here, here, and here. Now it has mirror plane, so there is a down pole. Upper pole is right hand, and down pole is left hand. So this one is C3H. This one can be written as 3 over M, because one axis has both threefold and mirror plane. In this case, this one has threefold, so it has 120 and 240-degree rotation operation. It doesn't have 180-degree rotation operation components in there, so there is no inversion center. Okay, as you see, there is no inversion centers. C4H, again, so there is fourfold, cyclic rotation operation of fourfold, and this one has mirror plane, horizontal mirror plane. So what you do is just 4 90-degree rotation operation, mirror plane makes down pole, left hand, and international symbol-wise, one axis has both fourfold and mirror plane. Okay, I will skip C6H. I want you to do it by yourself. Then basically what I finished is this part. Okay. Now C and I, just putting inversion center. CI is one-fold, just the inversion center. That's the same as 1 bar, international symbol-wise. And C3I is something that I will show you. C3I. Okay, C3I is cyclic rotation operation threefold, and it has inversion center in there. Okay, so strip projection stereogram-wise, now this one axis has threefold. Now it has inversion center in here. Okay, so if I do it, general pole, threefold, threefold, threefold. Now it has inversion center. Inversion makes this pole. inversion makes this pole, inversion makes this pole, and this is upper pole, again this is down pole, and this down pole is generated by the inversion center, right? Okay, so this one is left hand. Okay, what it looks like, C3I is like this, but this is just like a 3 bar. Okay, 3 bar is, in the previous lecture I explained to you about how you draw it, and if you draw the 3 bar, that's the same as 3 and inversion center. And 3-fold, whenever the 3-fold has inversion center in there, then that's we have to write down as 3 bar. It's not 3-fold, okay, it's a 3 bar. So I explained to you about this. Now let's put it NV. C1V, one fold is nothing, it's just one vertical mirror plane. It's the same as one mirror plane. So C1V is the same as CS, has only one mirror plane. Now let's look at C2V, C3V, and something like that. This part, I will draw one by one. C2V, what is this? This one is cyclic rotation operation of 2-fold. And it has vertical mirror plane. So let's put any vertical mirror plane in here. Vertical mirror. Champlain says that, okay, just simply put one vertical mirror plane to the symmetry operations. But in the principal theorem, we know that this 2-fold has a 180-degree rotation operation. So when there is a mirror plane, then in the plane which meets this plane should have mirror plane. This one should have 90-degree angle rotation operation. So extra mirror plane should be generated by the principal theorems, because the rotation axis has a 180-degree rotation. So the mirror plane should be at 90-degree angles. So mirror plane is developed, so you have to draw mirror plane like this. In the general pole, I have one pole here, 2-fold here. Now mirror plane generates upper pole, but this one is right hand, this one is right hand, but this one is left hand, this one is left hand. Because this one is generated by the vertical mirror plane. Now you immediately see that indeed there should be mirror plane at here, because this one is mirror and this one is mirror each other. Okay, so the symmetry element can be defined like this. So how we can define in the international symbol wise? International symbol, z-axis, principal axis as 2-fold. Now we have to define this mirror plane. Okay, this mirror plane should be defined by this axis. X-axis has mirror plane. And this mirror plane can be defined by this axis. So this is y-axis. Okay, so this is 2mm, meaning that x direction has mirror plane. The mirror plane is always defined by the vertical lines to the mirror plane. So x-axis has a mirror plane and y-axis has a mirror plane. So the international symbol of C2V should be written as 2mm. C3V as 3-fold. Let's put one mirror plane in here. Okay. Now, this is 3-fold. So the 3-fold has 120-degree rotation operation. So at each 60-degree rotation operation, there should be mirror plane generated. This is, again, by the principal theorems. So this one is mirror plane, and this one is mirror plane. So this is the symmetry elements of the C3V, cyclic, 3-fold cyclic rotation operation. You put the vertical mirror plane. Champlain says that just put the vertical mirror plane. When you put one vertical mirror plane, then by the principal theorem, all this one is basically mirror planes. All right? So for the general pole, 3-fold generates here, and 3-fold generates here. The mirror generates upper pole, but left hand. Mirror generates upper pole, left hand. Mirror generates upper pole, left hand. Now you immediately see other mirror planes are indeed there. Now international symbol wise, now this one mirror plane is defined. Now I can define this one x-axis as mirror plane. When this one symmetry wise, this one defines this mirror plane. Now this mirror plane is defined by these lines. Okay, now this one defines by these lines. This axis is this one defines by this axis. So how we write it international symbol wise? Now this one x, and now this one is x, and this one is x. Now another one should be defined as y, y, and y by the 3-fold operations. So if I write it, then it can be written like this. Okay. The international symbol wise, okay, principal axis as 3-fold. Now I can say that 3 x-axis as mirror plane and 3 y-axis as mirror plane. This one is x-axis as mirror plane and y-axis as mirror plane. But as you can see, basically x-axis, y-axis is the same because axis is defined by the straight lines. So you don't have to write down this m. So international symbol, this one is written as 3m. And now this 120-degree rotation, 3-fold rotation operation does not have 180-degree rotation operation components in there. Okay. So yeah, there's no inversion centers, of course. So this one is just write down as 3m. Now C4V, let me do it one more. C4V, again the same thing, simple, 4-fold. Now I put the mirror plane in here, vertical mirror plane. This one is mirror to the principal axis. Then this 4-fold generates mirror and mirror in here. But now remember that this one is 4-fold, so this one has 90-degree rotation operation. So extra mirror should be generated in here. Right? So mirror plane, in between the mirror plane, it should have 45 angle separations. So these are the symmetry elements of the C4V. And if I put the general pole, 4-fold generates here, and generates here. Now the mirror plane operation generates here. This one is left, and the mirror generates left, mirror generates left, mirror generates left. And you see again immediately that indeed there is a mirror plane in between these 90-degree mirror plane operations. So there is a mirror plane. There is a mirror plane in here, and there is a mirror plane in here. Indeed. Okay, international symbol-wise, how we define it? International symbol-wise, this one, we have to define this mirror plane. We have to define this mirror plane. So I have to define this x-axis, this x-axis, this x-axis, x-axis has mirror plane. In order to define this mirror plane, I have to define this axis. This axis has mirror plane. Always, mirror plane is defined by the perpendicular axis. So this one is mirror plane, and this one define this. You have to define this axis. Now you have to define these 4 axes. So international symbol-wise, this one is defined as 4m, 4 set of x-axis, and m, 4 set of y-axis. So this is the international symbol of C4V. Okay, if you do it, you will see C6V also has 6mm symmetry elements in the international symbol-wise.